All right. In chapter 15, we're going to be talking about acids and bases. So we're taking solutions a little bit further and going to be talking about acidity and alkalinity. So our acids, at the beginning of chapter 15 handout, we have properties of acids that we need to know. So acids typically taste sour, like lemon juice, for example. Taste sour, they dissolve many metals. They are going to produce hydrogen gas as they're dissolving metals. And then they're going to turn blue litmus paper red. So I'll get to this red equals acids in a second. But litmus paper comes in blue and red. And for blue litmus paper, acids are going to change it to red indicator. All right, for our bases. Bases taste bitter. For example, caffeine. Caffeine is a base that typically tastes bitter, and so we put lots of sugar in our drinks and things. Bases feel slippery. That is because bases, we see them in our soaps. So bases break down the oils on your skin or anywhere. And so basically, if they're feeling slippery, that's the oils in between your finger that are sliding around on top of each other. So that's why they feel slippery. Strong bases can eat at your skin like strong acids can, just FYI. And then bases are going to turn red litmus paper blue. So we have red and blue litmus paper. The easiest way to remember litmus paper changing and if we're dealing with an acid or a base. For blue litmus paper, if we have red, that means we're dealing with an acid. For red litmus paper, an acid is not going to change it to blue. So if we have red litmus paper and we're dipping it into an acid, it's going to stay red. Blue litmus paper is going to change to red. So anytime we see red, we're dealing with an acid. For blue litmus paper, if we're dealing with the base, it's going to stay blue. But if we have red litmus paper, we're changing to blue. So blues equals bases. Probably your easiest way to remember that is alliteration. So B, blue, B, bases. And then red is obviously acids. It's our only other color. So that's probably your easiest way to remember that. Okay, we have two definitions of acids and bases. So the first guy, scientist, chemist, who talked about acids and bases, his name was Arrhenius. So Arrhenius. His definition of acids and bases were that acids produce hydrogen ions. We refer to these hydrogen ions as protons a lot of the time, so I will use them interchangeably. So acids are going to produce hydrogen ions, and bases are going to produce hydroxide ions in aqueous solution. So basically, so hydrogen chloride is our example here. And if we have hydrogen chloride in solution, we are forming hydrogen ions, so here, and then chlorine ions. So if we're producing hydrogen ions, we're an acid. Hydrochloric acid is a very strong acid. And we'll talk about that in a little bit. And then bases are producing hydroxide. So sodium hydroxide is what we're starting with, and we're producing sodium ions and hydroxide ions in this solution. So our hydrogen and hydroxide ions are going to dissociate in solution. They're going to separate from each other and form cations and anions just floating around in solution. Okay, our protons are hydrogen ions. They're actually hydronium ions in solution. So if we have water around, that hydrogen ion, that proton, is going to combine with water, and we're going to form this hydronium ion. So 3 hydrogens attached to an oxygen. With that extra proton, that extra hydrogen ion, we're going to gain a positive 1 charge. All right, so the next guys, scientists, who came up with the theory for acids and bases were Bronsted and Lowry. So we got the Bronsted-Lowry definition. These guys realized that not all bases have hydroxide ions. So instead of talking about hydrogen hydroxide ions, Bronsted and Lowry were like, okay, let's talk about where the proton is going. So acids are proton donors. Their proton, their hydrogen ion, leaves that, that substance, that molecule. And then bases are hydrogen ion acceptors, so proton acceptors. So that hydrogen ion from the acid is going to go to the base. So for Bronsted-Lowry, we don't need hydroxide ions. That hydrogen, that proton is still super important, but not all bases have a hydroxide group in them. Okay, so your example here, hydrogen chloride plus water is going to give us a hydronium ion and a chlorine ion. So notice how this hydrogen ion here in hydrochloric acid is leaving, being donated to water, and it's going to form a hydronium ion. So the hydronium ion is, or the water is accepting that hydrogen ion. So according to Bronsted-Lowry, this is our Bronsted-Lowry acid, and then water is our Bronsted-Lowry base. Okay. So, next thing that we're talking about is we're talking about conjugate acids and base pairs. These guys are related to each other, plus or minus a proton. So related to each other by transfer of proton. We're either gaining a proton or we've lost that proton. But they have to basically be the same thing, plus or minus a proton. Okay, so for example here in your chapter handout. So ammonia, NH3 is our base. Notice how it doesn't have hydroxide, but it can still be the base. So notice in our products, our ammonia is turning into ammonium. So it is it's accepting a proton. Sorry. So that's why it's our base. It's going to accept our proton, forming NH4 plus ammonium. Water is going to be donating that proton. So that's why it's the Bronsted-Lowry acid. So notice how we've lost that hydrogen ion in our hydroxide here. So water has donated the proton to ammonia to produce ammonium ion. Okay, so our base and our conjugate acid, those two guys go together. So basically our conjugate acid is our base, but we've added a proton to it. So base and conjugate acids go together. We've added a proton, so that means we're dealing with an acid at that point in our products. For our acid is going to be become our conjugate base because we've lost a proton. So if we're losing protons, we're changing from an acid into a conjugate or related base substance. So our conjugate base is our acid minus a hydrogen ion. All right, let's look at example number 1. So example number 1. In each of the following reactions, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, and the conjugate acid and the conjugate base. All right, let's look at letter A. So with letter A, we have sulfuric acid plus water is going to give us hydronium ion, and then a hydrogen sulfate ion. Okay, so let's look at where our proton is going. So these two guys are related. They are either acid or base pairs. And then these guys, water and hydronium, are related. So notice in our product here with hydronium, we have accepted a proton. If we are accepting a proton, that means we are a base. We are a Bronsted-Lowry base. We're accepting the proton. Sulfuric acid, notice how we've lost a proton over here. So that means that we are donating a proton to water to form hydronium. So this is our Bronsted-Lowry acid. Which would mean our Bronsted-Lowry acid is going to have a conjugate base. So we've lost that proton. And then our Bronsted-Lowry base is going to form a conjugate acid in our and our products. So acids, conjugate bases go together, bases, conjugate acids go together. It's just, have we lost a proton? Did we gain a proton? We're just looking at where our protons are going, according to our Bronsted-Lowry definition of acids and bases. Okay, let's look at letter B. Letter B is a little bit more tricky, just because of what it looks like. So we have hydrogen carbonate ion is combining with water, and we're going to form carbonic acid and hydroxide ion. So let's look at where our proton is going. So these two guys here are related, obviously, and then water and then hydroxide are related. We're just plus or minusing a proton. So here in our reactant and here in our product, it looks like we've gained a proton, a hydrogen ion. So if we are gaining a hydrogen ion, that means that we are Bronsted-Lowry base. We have accepted, we are a hydrogen ion acceptor. So this HCO3 minus is a Bronsted-Lowry base because in our products we are accepting a proton, which would mean that our other reactant, water, is the Bronsted-Lowry acid. Our Bronsted-Lowry acids are the ones that are donating a proton, so we're going to be subtracting our proton. So that means that Bronsted-Lowry base is going to make a conjugate acid. They're related, plus or minus a hydrogen ion, and then our Bronsted-Lowry acid is going to produce a conjugate base. They're related, but plus or minus a hydrogen ion. All right, let's look at example number 2. So in example number 2, we are writing the conjugate acid of each base. So writing the conjugate acid. So let's think back to our notes from literally 5 seconds ago. Our conjugate acids are our base plus a hydrogen ion. So we are accepting a hydrogen ion to form a conjugate acid. So that means that we are just taking these 3 substances and adding a hydrogen ion. So HF, hydrofluoric acid, and then we have carbonic acid, and then our hydronium ion. Sorry, I forgot the charge there. Plus charge. Notice that we have negative charges here, and if we're adding a positive charge, we're going to be neutral. But with neutral water, we're adding a proton, so we're going to form a positive charge. All right, let's look at example number 3. So write the conjugate base of each acid. So conjugate bases are our acid minus a hydrogen ion. We're taking it away. We're taking away a positive charge. Which means that we're going to be forming a chlorine ion, chloride ion, Cl-1, hydrogen sulfite ion, HSO3 minus 1, so just taking away a hydrogen ion, and then CHO2 minus 1, just taking away that hydrogen ion. The only one that's going to be taken away is this guy here, the first hydrogen, not the one that's in the middle. For our acids, we're going to be taking away that first hydrogen. Okay. Example number 4. Identify the following as an acid or base and write a chemical equation showing how it is an acid or how it is a base according to Arrhenius. So remember back to our definitions. Arrhenius said that we're going to be forming hydrogen ions, H+, and hydroxide ions, so OH- for our acids and bases. Okay, so NaOH is a base. It's got hydroxide in it. That's the easiest way to tell if something's a base. It's got hydroxide, OH. So according to Arrhenius, we are separating. We are forming hydroxide ion, and then whatever other ion was with it. So we got sodium ion here. So hydroxide is going to dissociate, so separate into sodium ion plus a hydroxide ion. With letter B, we have sulfuric acid, H2SO4. It's a strong acid. Typically, our acids start with hydrogen, unless we're looking at water. Water, we have to be super careful, and we'll talk a little bit about that later, but it could be an acid or a base, like we saw in example number 1. So between letter A and letter B, it was acting as an acid or a base. So it's totally different. So that rule doesn't always work for water. We got to do a little bit more looking at for those. But typically if we're starting with an acid, or starting with hydrogen, we're going to be an acid. Okay, so according to Arrhenius, we're separating, we're forming hydrogen ions. So that means we're separating from the rest of it. So here we're producing a hydrogen ion and then HSO4 minus. So we actually technically have 2 hydrogen ions. So we could have 2 different things that we could look at. So we could have this, what I've written down, or we could have 2 hydrogen ions plus an SO4 -2 ion that's forming. If both of those hydrogen ions are going to dissociate, so separate from each other. Okay, let's look at example number 5. Which of the following are conjugate acid-base pairs? So remember, our conjugate acid-base pairs, they are related, but plus or minus a hydrogen ion. So let's look at these guys. In letter A, we have NH3 and then NH4 plus. So aren't they basically the same, but we've added a hydrogen and then a +1 charge? So these guys are definitely conjugate acid-base pairs. They are related, and we've added a hydrogen ion. Let's also look at whether it's an acid or a base, real quick, just to get more practice. So here we have NH3, and we are accepting a hydrogen ion. So according to Bronsted and Lowry, if we are accepting a proton, we are a base. So NH3 is a base, and that means that NH4 plus is our conjugate acid, according to Bronsted and Lowry. So NH3 is a base, and then NH4 plus, so ammonium ion, is a conjugate acid. Let's look at letter B. HCl and HBr. Chlorine and bromine are not the same thing. So they're not related. So these guys are not acid and base pairs. Let's look at letter C. So aren't these 2 things basically the same, just we've added this hydrogen here? Yeah, basically. We're also adding a hydrogen. So we are accepting a hydrogen ion. So this is a base. Our acetate ion is a base. And then we're forming acetic acid, which is a conjugate acid from our base. All right, last one, letter D. We have hydrogen carbonate ion, and then we have nitrate ion. Even though we've added a hydrogen, carbonate and nitrate are not the same thing. So letter D is not a conjugate acid and base pair. They're not related. Okay, let's look at neutralization reactions. So neutralization reactions, we saw these in the chapter with chemical reactions, where we talked about combustion reactions, synthesis reactions, decomposition reactions, single and double replacement reactions. Neutralization reactions are one of the types of double replacement reactions we talked about. So we talked about precipitate, and we talked about neutralization reactions with double replacement reactions. So in neutralization reactions, we are adding an acid and a base, typically a strong acid and a strong base. And we're going to be forming water and some type of salt. Most of the time, our salt is going to be soluble in our solution, which is what we want. Notice here the ionic compound that contains the cation from the base and the anion from the acid. That's what our salt is. So it's everything that's left over after we take out the hydrogen and hydroxide to form water. Okay, let's look at example number 6. So write the molecular equation for the reaction between aqueous hydrochloric acid and aqueous calcium hydroxide. Okay, so we need to follow the rules that we were doing when we were writing balanced chemical equations from names. and from reactants as well. So let's write the names of both of these. So instead of naming this hydrochloric acid, we're going to name it hydrogen chloride. Same thing, but hydrogen chloride is a little less correct. Okay, and then we have aqueous calcium hydroxide. So this is calcium hydroxide. Okay, so with a double replacement reaction, two things are going to be staying and two things are changing. So let's keep our hydrogen and calcium the same, and then we're going to switch our chloride and hydroxide. So in our products, we're going to be forming hydrogen something and then calcium something. So we're going to switch hydroxide and chlorine. So hydrogen hydroxide is one of our products. And then calcium chloride is our other product that we're forming. So we're just switching two things. Keep the first part of the name the same and switch the second part for our products. Okay, at that point, we can write our chemical formulas of these using the names. So hydrogen has a positive 1 charge, and hydroxide has a negative 1 charge. So these are going to cross charges and cancel each other out, and we get HOH, which is the same thing as H2O. Calcium chloride, so calcium forms positive 2 cations, and chlorine forms a negative 1. So we're going to be CaCl2 for calcium chloride.